Teardown time. This is the Amazon Alexa Echo Flex. It's the cheapest version in the Echo line. In fact, it was on a recent sale for all of $15, which makes it an irresistible teardown target. Okay, obviously a complicated module. We got a ribbon cable connecting two circuit boards. Speaker here, there's metal shields here covering all the exciting and interesting silicon. This is what's known as thermal interface material. It comes down and is touching these metal lids, so the cooling, you can sort of cooling effect here, and a much more significant metal can on this side, and a bunch of connectors. Well, let's take some detailed pictures. All right, so there's basically three main circuit boards when you take the full assembly apart. The main board on the leftmost side here, containing, of course, all these significant silicon. And we'll get to that. It's going to be a multi-part video here. There's so much silicon in this assembly to analyze. It's just amazing what I got for $15. On the middle assembly, we see the basically some sort of I/O board. The Echo comes with the option for a couple of add-ons. I think you can put a nightlight on. You can plug it at the bottom. That's what that USB port is for. And then on the top here, there's actually an audio jack, so you can add a external stereo amplifier and get much better quality audio. The Echo Flex definitely has a pretty modest quality speaker inside of it, but you can quickly resolve that actually if you have an external amplifier. And on the right, of course, as you might expect, a power supply. Appears to be a wide-ranging input power supply. It takes 110 to 240 volts on, and then it produces a single DC voltage, which then goes off to the assembly. All right, let's go into the main assembly first. Now, you might think I should dive into the main circuitry here, but just before we get to that, actually, I have to cast my eyes on the top portion of the board because it's actually kind of interesting, and they are sophisticated to say the least. If we just circle the two of them, there's multiple microphones. That appears to be consistent. All the Echoes I've ever torn apart have multiple microphone placements. I presume that buys them some huge advantage, because if you actually own an Echo, you quickly recognize how spookily good it is at listening to human voices and picking out a command, even in a noisy room. It's just amazing. Anyways, this is called a MEMS. It's basically a sensor that's built out of silicon, so they're pretty darn interesting to take a look at. There's a metal cap on at the top, and of course, with the metal cap, you might ask yourself, well, how do you get air pressure into it? Interestingly enough, the microphone's actually in the bottom of the assembly, so there's a hole cut in the circuit board, and that allows the air to enter through this drill hole and up into the actual sensor, bottom mounted. I presume there must be some sort of mechanical advantage in putting the sensor on the bottom. Now if we just zoom to the top of the board, we can see associated with the two microphones, one here on the left, one on the right, I've circled an analog to digital converter. So it tells me that the output of these microphones must be analog. And then we see what appears to be a TI 320 ADC 3101. It's a stereo ADC converter, and even more interesting enough, it actually has even a DSP function. So I suspect that silicon's going to be kind of sophisticated. Let's first take a look at the actual microphone. So as I mentioned, of course, here's the case with its golden color, and if you flip it over, you of course see again the microphone input is in the bottom of it. Now, if you take the lid off, basically, so I've desoldered it, you can see two assemblies in the middle here. You can see the actual silicon MEMS sensors. They're on the left here. And there's actually two of them. There's one transducer here and one transducer here. Interesting enough, they only bond out one. Now, it's going to this indistinct blob of epoxy, and that's because under there's going to be another ASIC. So silicon upon silicon in these assemblies. Let's see here. Let's just zoom into the actual MEMS because it's kind of fun to look at. This is a microscope photograph taken of it. Now starts to really get your secrets. Knowles is the manufacturer. Interesting enough, though, if you go into their catalog to their website, I can't find the actual assembly, so I'm not sure if this was built uniquely for the Amazon Corporation. You also see in the circle there a M in a circle rather than a C in a circle. That's what we kind of would expect, C for copyright. Masks under American law get a special mark called a mask mark, and it's an M in a circle, and that's what that's all about. And as you mentioned, two transducers here. They've only bonded out one for some reason. There must be some reason for that, I do not know, but Basically, the bond wire is coming here, and the sensor is in the middle, and it's basically hanging on in the frame here. And as air pressure is applied, it vibrates. And what happens is you apply a voltage. We're going to take that ASIC apart if we can find it, and it's going to have about 20-volt charge pump onto it. It basically applies a bias onto this piece of silicon, and then as it vibrates, you can actually use some signals conditioning to actually read out the output of the microphone. So let's take that next. Let's take a look at the actual silicon for the ASIC inside this microphone. Okay, well this is the integrated circuit that's contained inside the MEMS microphone. And I kind of suggest maybe be a charge pump producing that high voltage, but clearly that is not the case. That's a pretty time-honored way of creating about 20 volts. You just do a bunch of series of capacitors and diodes, but these are definitely not those. These are inductors, of course, all sorts. One here, of course, one here, smaller one here. And same thing on this side. Looks like they're probably, because it's meant for dual channel or stereo application, looks like these are sort of mirrored. And of course, you want to create a high voltage with an inductor. Of course, that's very easy. You put current into it, let the field collapse, and then rectify it. And it's certainly a time-honored way also of creating a high voltage. And then in the center here, my goodness, piece of artwork, isn't it? Almost looks like an impedance matching transformer. So I think there must be a few transistors sitting in this piece of silicon, but I must say this isn't quite what I expected at all. It's quite unusual. It has a die mark CG60173A1. I must admit, I do not think that matches anything I could find on the internet, but there you go. So that MEMS microphone, obviously that very sophisticated piece of silicon, and then a really neat looking bit of analog silicon backing it up to create the signal that goes out into the ADC converter. Alright, this is the die photograph of the ADC converter. It's a dual channel design. You can of course see that very quickly when we look at a die. You sort of draw a line down the middle here. You can see that the blocks match. This block looks like this block, and that block looks like this block, and this block, of course, looks like this block. That's because it's a dual channel, and that makes sense. Now, just to poke down what we're seeing here, let's go to a different slide, the block diagram from the vendor. It's got an analog input with switching attenuation. Then there's the ADC converters, and then there's a very sophisticated DSP block. And then you can see a bunch of peripheral functions, phase lock loops, I2C controllers, and such coming down here. Let's just pop back up to the previous screen, see if we can sort that down. The bottom portion is the analog. Here is basically the analog portion of the design. And you can see that because if you were to just zoom in, these blocks here are capacitors, and down here you can see some large transistors. Here you can see some large transistor structures, so quickly it becomes evident. It's a digital section on top here. Basically this is the DSP. It's been laid out as a series of gates. The only hard macros you can see, there's one here and one here. I suspect the top here is the ROM, and there's the RAM down here, a scratch pad RAM of some sort. So, much the same on this side here, the second channel laid out similarly. It's not quite symmetric, because I suspect there's over here some of the utility functions on this side of the chip coming down here. Anyways, ADC converter, of course, also more than just simply a converter now. Doing a lot of signal processing before it gets passed into the main SOIC. Alright, well here's all the main bits of silicon that we're hiding under those metal cans. The item in red is the main controllers from MediaTek. If you haven't heard about them, they claim to be the 4th largest fabless semiconductor manufacturer in the world. And I would believe that. They have a huge selection of parts, and when you get designed into something like an Amazon Echo, you are probably shipping some pretty serious volume. Quad-core ARM A35, that is a huge amount of compute power. I think each core is rated at 1.4 gigahertz. Wow, you look at the gigamips of processing power. And of course, that's what makes these things possible, the ability to get, for only a few dollars, giga transactions per second in your processor. Associated with the SOIC, which is this red thing, MediaTek, is the DRAM. Not too much surprise there. That's for, of course, temporary data store. And then the actual program stored in this yellow device called a NAND. Same thing, and then it's attached to the MediaTek. Up here was that Adc Converter, and of course it's going to be connected into the MediaTek. It also claims in the datasheet to have all sorts of audio processing. Huge surprise, because of course that's what this device is all about, processing voice. Interestingly enough, it even has the video output, apparently HDMI. I think there's echoes out there with screens on them, of course, not used here, but sometimes cheaper to use the same piece of silicon no matter what. Now, the other thing that's kind of interesting is that this item in red, the main SOIC, claims to have a Bluetooth interface into it. Pardon me. It claims to have a Wi-Fi interface built into it. But over here is a separate chip, also from MediaTek, which is a dedicated Wi-Fi and Bluetooth. So for some reason, even though this chip here already has an RF interface, it looks like, especially when you look at the board here, right, they see there's two antennas, and they come up, and they come into the blue chip here, so then around. And there's no antennas that I can see attaching to the red SOIC. So, okay, let's take a first look at the silicon in the main SOIC. And for that, we'll take that package off, and we get what's shown here. This is what's known as the top metal layer, and it made it look too exciting, and that's quite true, actually. You get these primary interconnects. These things here would go to metal balls that would then go on to touch the substrate. But all the area around here is basically silver, and that's because it's a metal patterning, and it's hiding basically the logic below that. So we can't see right now the ARM processor and such. We can see some things though, and I'll go to a different picture here in a moment. Basically all the hard macros, these are the high-speed peripherals, and they usually sit at the edges of the chip, except for the processor cores. Down here is definitely an RF core, for example. Basically these are the blocks that you would purchase from a vendor, and you just drop them down in your design, basically. And then under the silver here is basically all the logic the customer provides, and it's compiled down by the compiler, and then it's laid out as a sea of gates. Here's a different picture. It's actually a mosaic taken by my microscope, and that's why it has a ragged edge there on top. But now we can start to more clearly see some of the actual structures. This one here especially, let me just actually go to the next page on the presentation, because I zoomed into it. I'm pretty sure, well, not pretty sure, I know for certain this is an RF function. You can always tell RF functions by these inductors here. Here's a transformer, and another one, another transformer. Parts of PLLs, mixers, and the actual antennas. Actually, pardon me, not the antennas, but the mixers and the phase lock loops need inductors to function correctly. This almost certainly is a Wi-Fi section down here in the actual chip. And if we come back up, what else can we see? We can see some of the I/O to the DRAMs and to the NAND coming down on this side of the chip here. But to go further, basically what I have to do is now known as a metal strip, and that takes a bit of time. But I have to remove the metal here for us to figure out what's going on the chip. And I think that's going to be worthy of the next video. With so much silicon on this chip, I think this is going to definitely be a multi-parter. So hopefully that's of interest. If it is, please leave some comments in the video so I can maybe adjust my second video to touch upon things that people are finding especially interesting. Or if there's things that you really care for, tell me that as well, actually. I do love that feedback. Quite enjoy it. Anyways, till next time.